Coming up on Dr. Kiki Science Hour, we're talking about neutrinos and the Pauli exclusion principle with Sean Carroll from Caltech. That's up next on Dr. Kiki Science Hour.
Netcasts you love.
From people you trust.
This is TWiT. Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki's Science Hour with me, Dr. Kiki, episode 134, recorded Thursday, February 23rd, 2012. From eternity to a faulty cable. This episode of Dr. Kiki's Science Hour is brought to you by Netflix. Watch thousands of TV episodes and movies on your PC, Mac, iPad, iPhone, or TV instantly, all streamed directly to you, saving you time, money, and hassle. For your free 30-day trial, go to netflix.com/twit. Welcome, everyone, to Dr. Kiki's Science Hour. I am Dr. Kiki Sanford, and this is the hour that you get to sit back and relax and enjoy an entire hour of science. That's right, talking about a topic in the sciences with an expert in that subject for the entire period of the show. This is not about sound bites, people. This is about learning. It's time to get your learning on. So I hope that you are ready to dig deep into the knowledge, the learning that is the science of faster-than-light neutrinos and getting the science right when it comes to quantum physics with our guest, theoretical physicist Sean Carroll. But first, a few science headlines. It's February 23rd, 2012, and this is the science that made headlines this week. According to news from CERN, the OPERA collaboration has identified two possible factors that could significantly affect the faster-than-light neutrino result. Both are related to the GPS timing system in use, but point in opposite directions. So new experiments are to be expected that will either negate or enrich our understanding of the FTL neutrino phenomenon. A new paper in the journal Animal Cognition describes the final experiments run on Alex the parrot before his death in 2007. The studies investigated his math abilities and found that Alex was capable of adding numbers up to a maximum sum of 8 and of adding the numbers of objects presented to him sequentially. Known previously for his amazing language skills, this research suggests that Alex might also have been better at math than chimpanzees and other non-human primates. Pretty cool. You might have heard something about the slowly dying Y chromosome at one point or another. Well, gentlemen, you're off the hook. The Y chromosome is probably here to stay. According to a study published in Nature, the Y chromosome will most likely be around millions of years from now, thanks to a genetic sequencing study looking at genes in the Y chromosome. Researchers have created a compound called QAQ, looks a little bit like quack, that can inhibit pain at the flip of a switch. The molecule has two functional parts connected by a light-sensitive bridge. One part resembles lidocaine and can interact with ion channels to change nerve sensitivity. So far, it has only been confirmed to work in animals, but the researchers hope to find ways to apply it to humans. Circadian rhythms were definitively linked to cardiac arrest by researchers at Case Western Reserve University School of Medicine. The study links a lack of a novel genetic factor called Kruppel-like factor 15, or KLF15, to a loss of electrical activity to the heart, which can lead to sudden cardiac death due to arrhythmia. Data from the multi-angle imaging spectroradiometer on NASA's Terra satellite indicates that clouds are getting lower. In fact, from 2000 to 2010, average global cloud height changed by 30 to 40 meters, mainly a result of fewer higher altitude clouds. So really, they're just getting lower. However, it is still unknown what effect, if any, this is going to have on global warming and climate change. Michael Houghton of the University of Alberta, who discovered hepatitis C, announced that he has created a vaccine that is effective against all strains of the virus in the lab. The vaccine still needs to successfully pass all clinical trials before becoming available for human use, which, if all goes well, could be in about 7 years. And time is of the essence, as Hep C now kills more U.S. citizens than HIV. A team of scientists described a process that might be called a pulse of the Earth in the Journal of Geology. They showed that strontium-87 records increased in marine fossils with the same periodicity as massive marine extinction events that occur every 60 million years. They suggest that a process called continental uplift or tectonic uplift occurs, increasing continental elevation and decreasing sea levels enough to make coastal living difficult for marine organisms, which would lead to the massive die-offs. And that does it for the science headlines this week. Let me know what you think about these science news stories, or tell me what you think should be news by emailing Dr. Kiki at drkiki.tv. Or you can leave me a voicemail at 650-741-5454. And now I'd like to thank Netflix for sponsoring this hour of Dr. Kiki's Science Hour. Netflix streams thousands of TV episodes and movies directly to you instantly, which means that you save time, money, and hassle. There are several ways to instantly access streaming movies and TV shows with Netflix. First, you can watch Netflix movies and shows on your Mac, your PC, your iPad, if you've got the Netflix iPad app, your iPhone, and even some Android phones as well. So you can be at your desktop, your media center computer, or on the go. It's pretty great. If you have a gaming console, an Xbox 360, PS3, Nintendo Wii, you can use one of those to watch Netflix right on your TV. And there's some cheap, easy-to-use alternatives like the set-top boxes, Roku box, or the Apple TV that are available as well with Netflix. With Netflix, you can watch movies and TV shows instantly with any of these devices. And the cool thing is you can stop watching your show or your movie at any point and then start watching it on another device at the same point that you left off. It makes it a seamless experience wherever you choose to watch Netflix. And whichever way you want to access Netflix, you can watch as many movies or shows as you like anytime you want. And you can cancel anytime for free. So try Netflix today. 30 days, absolutely free. Just go to netflix.com/twit. Make sure you use this URL to sign up and take advantage of this offer to get your 30-day trial. Netflix, netflix.com/twit. We thank Netflix for their support of TWiT and Dr. Kiki's Science Hour, and hope that you enjoy watching instantly with Netflix. Now let's get into the show. We've got a guest here that I'm excited to be speaking with. He has written several books, and according to him, is in the process of writing a new book, which I'm rubbing my hands in anticipation for. Sean Carroll is a senior researcher in the Department of Physics at Caltech, California Institute of Technology. His research interests include theoretical aspects of cosmology, field theory, and gravitation. He's the author of a graduate-level textbook, Space-Time and Geometry, an Introduction to General Relativity, as well as a set of teaching company lectures on dark matter and dark energy. And his latest book, From Eternity to Here, The Quest for the Ultimate Theory of Time, explores the relationship between entropy, cosmology, and the arrow of time. You can also see his blog posts, which he updates fairly regularly at his blog, Cosmic Variance, at the Discover Magazine blog's website. Sean, thank you very much for joining me on the show today.
Thanks for having me, Kiki. Good to be here.
Yeah, it's great. There's big news this week in physics. Maybe an end, maybe a new beginning to, or this a continuing chapter in the saga of the faster than light neutrino.
Yes.
You're rolling your eyes. You're rolling your eyes a little bit. Can you give us a little bit of background on this story? It was last fall that the faster than light discovery was first made.
That's right. So last fall, there was an announcement, both a technical talk and a technical paper and a press conference and the whole big deal from a collaboration called Opera. It was a group of Italian scientists, and what they did was they took neutrinos that had been generated at CERN, at the Large Particle Accelerator outside Geneva, and they shoot the neutrinos they create at CERN under the ground because neutrinos basically go through matter and almost never interact. So they can just fly through the mountains until there's a big neutrino detector at the Gran Sasso laboratory in Italy. And then you look for various properties. Usually physicists are looking for, do the neutrinos change from one form of neutrino to another? That would tell us about their masses and their interactions. But what this experiment did is it just calculated the speed at which the neutrinos were moving. If you know what time it left and you know what time it gets there, you divide by the distance, and you can get the distance divided by the time, rather, is the velocity.
Right. We learned stuff like this in introductory physics or introductory algebra, where you're calculating the speed of a train, right?
It really is just speed is distance divided by time. That is as complicated as it gets. As long as you're measuring the speed and the distance and the time very, very precisely, you get a very, very precise measurement of the speed. And to their great surprise, they found that the speed was slightly greater than the speed of light. And you might say, well, how sure were they? How big was the effect? And we often, in physics, we talk about sigmas. A 2 sigma effect is no big deal. 3 sigmas is getting interesting. 5 sigma is a discovery that you can go home with. But what the sigmas are telling you is this just a statistical fluke, right? So if you get a lot of sigmas, then you know it's not just a statistical fluke, that something real is going on. And the Opera experiment said that at the 6 sigma level, these neutrinos were moving faster than light. So what that means is it's certainly not a statistical fluke. Of course, it can still be a mistake. You can still be doing something wrong. And because this is a very difficult measurement to make, and because it violates everything we think is true about relativity and so forth, most people, including myself, went to their Twitters or their blogs or whatever and said, look, this is very interesting. The experimenters are respectable people, but it's probably not true. We'll have to obviously wait until we get some tests, to see if they did goof, or someone else does another experiment and gets the same result, in which case, it's a full employment for theoretical physicists such as myself to figure out what is going on. So the update now we got is that they might have located a goof or a couple of goofs that they could have made. There was a short, difficult to interpret 1-paragraph press release that they released saying they put their finger on at least 2 things that could have been going wrong. They won't tell us whether those 2 things are sufficient to explain the effect. But the rumor is that, yes, that they are sufficient to explain the effect. And because there was an overwhelming belief that it's very unlikely that neutrinos move faster than the speed of light, most people are going to be willing to believe now that somehow one or both of these mistakes is responsible for what we thought the signal was.
What is the likelihood of these mistakes? I mean, do you have any insight into what they've been doing, and I mean, a loose cable is. I mean, that's cable. In fact, really?
Well, again, there's sort of levels of well-sourced information. The actual press release from CERN doesn't say very much. It does talk about the connection between a timing apparatus and the experiment, which could be interpreted as, a cable was loose or something like that. The difference in times between the speed of light and what they measure is something like 60 nanoseconds. I forget the exact number, but it's something like that, which is a few meters worth of cable that they didn't take into consideration. So that doesn't sound right, that you would forget a few meters worth of cable. On the other hand, the experimentalists I've talked to when the result first came out, the first word out of their mouth was cables. Cables are often the thing that goes wrong in these circumstances. And we should point out that this kind of experiment is not what particle physicists usually do. It's not in their wheelhouse. They're usually looking for, like we said, particles changing their identity or interacting with other particles. This type of physics experiment, precision measurements of times and distances, is a whole area of physics that people specialize in and take decades to become expert at. And it's very hard. And it's because anything that you buy, any piece of equipment you buy off the shelf, if there's a tiny little mistake in it, it can completely give you the wrong answer for your experiment.
So with this experiment, they repeated the experiment and said that they found similar results again towards the end of 2011. Wouldn't they have if people after the first telling of the results said, cables, wouldn't they go back and go, okay, is everything connected right? We'll make sure everything's connected. Look, same result.
Well, you would think so. I don't know what it means when they said that they did the experiment again. If you are doing something wrong and you do it 5 times, you're still doing it wrong. So, I think it is. I have to say that many of us, including myself, our attitude at the beginning was, it's probably wrong, but these are very good experimentalists. They know what they're doing. They're not crackpots. We should, take their word for it that they're doing the best they can to find the mistakes. But there is an extra layer of responsibility, I think, if your result is something is moving faster than the speed of light. I think that, given that they really weren't under competition with anybody else, I think an argument can be made that they should not have released a result until they had literally torn the whole thing apart and built it up from scratch anew and tried again. They probably thought that was a very difficult thing to do because, it takes time, it takes money. The neutrinos are, when CERN can send them, they're not just always there. So they might not have had the opportunity in their minds to actually do that. But I think that, other people in the precision measurement game have learned the hard way that if you get a result that violates everything you know about the universe, you do everything you possibly can to find out where you might have made a mistake before you hold a press conference. Right.
Yeah. The science by press conference is not necessarily the best way to go about science. However, and we've seen that happen in the public science of the arsenic life story that's been playing out over the last couple of years as well. With this story, it seemed as though the researchers were really just kind of stumped and just reaching out for help. Not saying they never said we think this is right. They just said, we got this. Help us.
No, that's right. I mean, I do give them a lot of credit. They were not out there for the glory. They were not saying that they had overturned Einstein. They were saying, look, this is a puzzling result. Frankly, several of them said, we don't believe it ourselves, but we've done the best we can and we can't find where it was wrong. And so maybe now with some extra effort, they have found where it is wrong. So I don't think that they cut corners because they wanted to get a certain result. Really, if you get a result like this when doing an experiment, you almost don't want to get it because you know that it's probably not right, and you can see what's going to happen, right? You're going to send it out there, people will make a big deal about it. You're going to find a mistake, and you're going to look dumb 98% of the time. Because I've been talking to other physicists around here at Caltech and trading stories of, basically every year there's been something like this. Someone discovers something and then it goes away. In astronomy and particle physics, in all sorts of different areas. So it's a tough, it's a tough game, but I don't think that it is in any sense because the experimenters weren't trying their best or wanted in some sense to pull one over on us. I think that, they just, were doing the best they can, but there was a mistake. And maybe it's easy for me to sit here in my office as a theorist and say they should have tried harder.
Right. Just try harder. Do the experiment a little better.
The press conference thing is interesting. I don't mind that they had a press conference if they crossed the threshold where they said, look, we've done everything we can. This is the result. It's worth a publishable paper. We can't think of anything else to test. If it's worth a publishable paper, then it's worth a press conference because we're in an age now where you don't do science in private, right? Everything is out there. There are not just the papers going onto the internet, which is certainly the case, but then there are blog posts and tweets and articles in the newspapers. So I don't mind a press conference at all. If they made a mistake, which I'm not in a position to say, but the mistake was they didn't check their cables quite as thoroughly as they could have. It's not that they held a press conference.
I love the language from the press release, though, that they say there are two possibilities point in opposite directions. And what that implies to me is that one of the errors might negate the result, and that one of the errors might actually increase the distance, the time.
That's right. Yeah, I think it'd be hilarious if after all this they come back and say, it's moving even a little bit faster than we thought that they were, these neutrinos, now that we've worked it all out. But, again, these experiments are not done in a theoretical background, in a theoretical vacuum, sorry. They are done with a theoretical background. Extraordinary claims require extraordinary evidence. And so if there is any mistake being made at all, the chances are not 50-50 that it makes the effect bigger or smaller. The chances are 99.99% that it's going to make the effect go away.
Right. And for the story of what's happening, if it were the faster than light neutrino, can you just in a nutshell explain how it would overturn all of physics?
Yeah, and that's
basically the soundbite that everybody in the news was using. It'll overturn all of physics. Really?
I think that's the wrong soundbite. The right soundbite is it will be the most important discovery in physics since the invention of quantum mechanics anyway. Probably more important than any single experiment that was done in the 20th century in physics, let's put it that way. Because it's so unexpected. It's much more expected than dark energy was in the acceleration of the universe. But that doesn't mean that everything we thought was true is now false. It doesn't mean that we know nothing about how the world works. It's clearly a very subtle effect, even if it were true. It's not something that affects most particles of nature. So what you do is you set out to inventing a theory. How to invent a theory that both incorporates the successes of relativity that we know are there and allows for this deviation from relativity. It's not even deviation from relativity, but this deviation from our expectation for the behavior of matter in the neutrino sector. So relativity doesn't say that particles can't go faster than light. Relativity says that particles either go faster than light, slower than light, or at the speed of light, and they never change what they do. If you're a particle that goes slower than light, then you only ever go slower than light. If you're a particle that goes faster than light, then you only ever go faster than light. And we've never found particles that go faster than light, so we don't think that they exist.
Right.
If they did exist, it would certainly the reason why people make grandiose statements is because we use the slower than lightness of ordinary particles in understanding how causality works in physics. Signals, certainly we don't want signals that can actually go into the past and affect something that happened yesterday.
Right.
And in the context of relativity, it's everything must move at or slower than the speed of light, which guarantees that is true. So what we would want, if the neutrinos did move faster than light, is to improve the theory so that neutrinos could move faster than light, but you still couldn't send signals backward in time. And that would certainly require a modification of our current ideas of relativity, and that would be a lot of fun for theoretical physicists. Sadly, it doesn't look like it's going to happen.
Yeah. Well, we will wait and see if there's, I guess, more news out of CERN and whether or not they come clean with exactly what happened with this experiment and what these faults might be.
And there is, we should say, another experiment at Fermilab outside Chicago, the MINOS experiment, that is trying very hard to test the result, to do a very similar thing. They shoot neutrinos to Minnesota, and they observe them in a laboratory there. So that's really what you need, is an independent, start from scratch, different experiment that does the same thing.
Yeah, that'll be really interesting. And I know that they had actually found they had not Six Sigma results, but they had data that was interesting in a similar, difference between the neutrino speed and light speed in a previous experiment. So I know that there is data out there.
That's right. These guys at MINOS, the Fermilab experiment, did, calculate the speed of their neutrinos. And if you just calculated the speed, they got an answer that is slightly faster than the speed of light. But they also have error bars. There's a significance to it. And the error bars on their measurement were more than big enough to say that the speed of light is perfectly consistent. There's no evidence that they really were going faster than the speed of light. So they didn't make a big deal out of it because there's no theoretical reason to expect that. So given the impetus that they got from the people at Opera, now they're going to improve that precision by quite a bit, and we'll see what happens.
I'm waiting. I still think this story. I think this story is not yet over. I think the experiments are still happening and still coming in, and this is maybe an interesting twist in the tale that's going to be told of the faster than light neutrinos when all is said and done.
Don't go around betting anybody because I don't think they're moving faster than the speed of light. So
yeah. Yeah, probably not. It's highly unlikely. In other news, you've also been you had a blog post that you posted today, in which you take Brian Cox, the rock star physicist from the UK, to task.
Literally the rock star physicist. He was in a
band.
That's a different kind of rock star physicist.
Yeah. You take him to task for the language that he uses to describe a particular aspect of quantum theory, the Pauli exclusion principle. And while that seems a little bit esoteric and maybe out of people's understanding, what is the Pauli exclusion theory? I thought maybe we could talk a little bit about it because I believe that the story, the fact that you're kind of talking about what he's saying and how he's saying, I think that this is going to reach a broader audience. And so we want to know exactly what's going on.
Yeah, I mean, I think the most important thing to say is that Brian, among other people, but he's one of the best, does an amazingly good and important job at explaining science to a very wide audience and getting people excited about science. So I'm a big fan. And that event that the original video clip was taken from is an amazing kind of event that we so much wish we had more of here in the United States, where it's a night at the Royal Society where he's doing a lecture and a set of demonstrations about the fundamental nature of reality. And there's celebrities and actors and people in the audience. And it's just so much fun. And so, incredible credit to him for doing it. So we're quibbling about one little thing that he said. And I don't want to lose the overall credit that I give him in the tiny little bit of quibbling that we're doing. And in fact, I wouldn't have done any quibbling at all, except that other people started blogging about it. And I think that there is some reason to talk about it because it's interesting physics to learn, to think about in doing it.
It's a teaching moment.
A teachable moment, yes, a teaching moment. So the specific claim that he made was that the Pauli exclusion principle, which is very, very important, it says that two fermions, two matter particles like electrons, neutrinos, quarks, whatever, cannot be in exactly the same quantum state. So this is what makes important things such as chemistry impossible. If it weren't for the Pauli exclusion principle, every electron in an atom would be doing the same thing. All atoms would basically be the same. You wouldn't have chemistry, life, anything like that. Because of the exclusion principle, as you add more and more electrons to an atom, they need to do like more and more twisty things so as not to be in the same quantum state as the other electrons. And that's what makes life literally interesting. So that's true, and he explains that, and he says it's true. It's responsible for the stability of matter, the reason why your table doesn't collapse, which is also true. Mm-hmm. But then he sort of mingles that true and interesting thing with another true and interesting thing to get a not quite true statement. The other true and interesting thing is that in quantum mechanics, when you have an electron, there's no such thing as the position of the electron. There's something called the wave function, which tells you where you might find the electron. What is the probability of seeing it if you look for it in a particular place? And the thing is that in quantum mechanics, if you solve the equations, the wave function, even for any particular electron, is spread out all throughout the universe. There's most of it right here in this atom that it's in, but there's a tiny bit of that electron that has the wave function of that electron that is everywhere, over in Alpha Centauri, that is in the Andromeda Galaxy, etc. There's a tiny but non-zero probability that you would see it if you looked. Very, 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 very tiny, but not quite zero. So he says what that means is that if I do something here to the electrons in an object, like he had a diamond, this is the benefit you get of being a rock star scientist. They give you diamonds to do your demonstrations instead of pieces of wood. But it's the same thing. You heat it up, you change the electrons here in the diamond, And he says that because of the Pauli exclusion principle, now every electron in the universe has to shuffle just a little bit in response to the changing energy levels inside the piece of diamond.
Why don't we can actually run the clip and watch it and see what he says.
Oh yeah, sure, that's great. This is good.
I think
this is not it.
This is not it. It's from the blog post. There was a short clip that one. That's the one.
So this is a diamond-sized box of carbon atoms. And here's the thing, the Pauli exclusion principle still applies. So all the energy levels in all those 3 million billion atoms have to be slightly different in order to ensure that none of the electrons sit in precisely the same energy level. Pauli's principle holds fast, but it doesn't stop with the diamond. See, you can think of the whole universe as a vast box of atoms with countless numbers of energy levels, all filled by countless numbers of electrons. So here's the amazing thing. The exclusion principle still applies, so none of the electrons in the universe can sit in precisely the same energy level. But that must mean something very odd. See, let me take this diamond and let me just heat it up a little bit between my hands. This is gently warming it up. I'm putting a bit of energy into it, so I'm shifting the electrons around. Some of the electrons are jumping into different energy levels. But this shift in the configuration of the electrons inside the diamond has consequences, because the sum total of all the electrons in the universe must respect Pauli. Therefore, every electron around every atom in the universe must be shifting as I heat the diamond up to make sure that none of them end up in the same energy level. When I heat this diamond up, all the electrons across the universe instantly but imperceptibly change their energy levels. So everything is connected to everything else.
So everything is connected.
Everything is connected, and it's true. So there's like another true statement that is sort of in there in the jumble, which is that in quantum mechanics, the world is described not as a state of this electron plus a state of that proton plus a state of this neutrino separately. In quantum mechanics, there's one state for all the particles in the universe. And as I say in the blog post, if you're modest, you call this the many-particle wave function. If you're not so modest, you call it the wave function of the universe. That's what Stephen Hawking would call it. But the point is that what does happen to one electron can, in principle, affect what you would call the physical properties of some other electron. So but the clear implication of the way he says it in the video is misleading, because he talks about the Pauli exclusion principle saying that two electrons cannot be in the same energy level. And that's not what the exclusion principle says. It says two electrons can't have exactly the same quantum state. So the two electrons in a helium atom have exactly the same energy level, but they have different spins, so they're not in the same quantum state. An electron here can have exactly the same energy as an electron in the Andromeda galaxy because it has a different position, so it's not in the same quantum state.
Right, because it's not in the Andromeda galaxy.
Yeah, I mean, it's
place in the universe.
So they're clearly different states.
Yeah.
And from the way that he put it in that video, it sounds like when you change the energies of the electrons in the diamond, the energies of everything else has to change because the Pauli exclusion principle says so. And that's not right. There is something that is close to being right, which he doesn't say, but I think he's thinking, and he's trying to translate from the equations into English, which is that if you change the conditions in this room, because the wave function of every electron in the universe stretches throughout the universe, you do change the state of that electron in some way. The problem is that if you are really in Andromeda and you have an electron that is mostly in Andromeda, there is nothing that you can do to detect this purported change. Any change that you would actually be able to measure requires the signal propagate at the speed of light. It's nothing instantaneous at all. So I think
so. It's not like an action at a distance type of thing where
no. So I would say it's wrong both technically, and it's wrong in the sense that because it's not the Pauli exclusion principle at all, and it's also wrong that it gives you the wrong impression. You know, I'm willing to forgive the technical simplifications because that's just necessary when you talk about some of these concepts. But what you then are aiming for is to get the correct idea into people's brains. And I think in this case, the idea that gets into people's brains is that by rubbing a diamond here in this room, in principle, there's a change that happens instantaneously in the Andromeda Galaxy. And even in principle, that's not true.
So what is true?
What is truth? Is reality in the world?
Yeah,
well, there are very interesting issues in the interpretation of quantum mechanics. And so in the blog post, I talk about what I think he really did have in mind, which is that just changing the physical conditions here changes the energy of everything in the universe. There's another very closely related issue that he doesn't talk about, and I don't think he was thinking of, but could be related, which is entanglement. Quantum mechanics says that there can be a correlation, an entanglement between the state of a particle here in this room and a state of the particle arbitrarily far away. It's actually difficult to maintain these correlations without ruining them, because if they bump into something, these correlations go away. That's why it's difficult to build a quantum computer, for example. But still, in principle, we're happy to talk about things that are in principle. Thought experiments are our stock in trade. So it can be the case that you have an electron that could be in one of two energy levels, and your friend in Andromeda has an electron that could be in one or two energy levels, and you don't know which one it is, but you know that the two electrons are in different energy levels from each other, which means that when you measure one, you instantly know what the person Andromeda would get if they were to measure theirs. Mm-hmm. However, it's useless to them because they don't know what answer you got. They don't know what the answer is until you send them a signal, which of course travels at the speed of light. So philosophers and physicists have a lot of fun arguing over the best words to use to describe this situation. Nobody argues over the physics of it. No one argues about what the experimental results would be. Those are crystal clear. People argue about what it means, what the right ontology to use to describe the situation is. And it's good that they argue about that, because hopefully by arguing about that, we'll come to a better, deeper understanding of what's really going on.
So with what Brian was trying to put forward, he claimed that it was to do with the Pauli exclusion principle, but that's probably not the case of what he was talking about. So he was talking about stuff that is correct in theoretical physics and in quantum theory, but not in what he was putting together.
Well, yeah, I mean, every individual idea that is in this bag is true, right? There is something called the Pauli exclusion principle. It is responsible for the stability of matter in the universe. Wave functions of individual particles are spread out over all of space. A change in the wave function at one point does change the wave function everywhere. All of these are true statements, but the particular order in which he put them in and the consequences that he drew from them, I think, were the wrong lessons.
So let's talk a little bit about the lesson and the science communication aspect of it, in terms of who he's trying to reach and what he's trying to do, and how accurate do you think things need to be for the general goal of science appreciation, science awareness to increase?
Well, I think, that's a very, very good question. The utopian situation is one in which everything you say is absolutely rigorously correct from any possible technical critique and increases the understanding in the mind of the listener. But getting both of those to happen is very difficult, and basically you're going to be a physics student and take, years of classes before you get there. So I'm happy when either one of those things happens. If you say something that is absolutely technically true, then at least you can, go to sleep at night, even if you didn't convey any information to somebody else. But I think it's absolutely fine to say things that are not absolutely technically true if the impression that the person gets when they're listening to you is a closer approximation to reality than the one they had before they were listening to you. So, for example, like I said, quantum mechanics has issues of interpretation. When you observe something, does the wave function truly change instantaneously throughout the universe, or does it actually evolve smoothly? This is a legitimately open question among physicists and philosophers who think carefully about this. Now, I would say that I don't need, every time I talk about quantum mechanics, to include a footnote saying, by the way, some people disagree and have a different interpretation of quantum mechanics. I think that it's okay in a popular talk or book or whatever to talk as if one of these interpretations is simply true and to be logically consistent within it. And hopefully the people listening will come to a better understanding. I mean, at a much simpler level, we have arguments like this about the question, is the redshift of distant galaxies due to the expansion of space, or is it because the galaxies are moving away from us? Right? This is no one denies that distant galaxies are redshifted. We can predict it and we can measure it. And no one denies what the equations are that are used to predict it. We just have different words we like to attach to the equations. So pick one. I don't care. I'm not going to disagree with you if you pick one and then try to explain this phenomenon to people who don't know the equations. That would be very, very ungenerous of me to say, well, you didn't pick my favorite words to describe this thing. But the words have to have some connection, right? And what we really want is for people to come to a better understanding of the universe through whatever words it is you choose to use.
Yeah, and hopefully the understanding of the universe will be more and more accurate, that the words themselves are giving a more accurate
I think that the one mistake that can be made is when you give people the illusion of understanding. When you give some set of words that people
analogies
go, oh, yes,
tend to do
sense. That. Even though they're not true, the words that you say. To me, a common example, when people talk about the acceleration of the universe, they sometimes say something like this. They say, well, dark energy fills the universe. Dark energy has a negative pressure. Pressure contributes to the expansion of the universe, so a negative pressure is kind of like anti-gravity, and that makes the universe push apart and accelerate. These are words that you will hear people say.
Right.
And they're not false, these words. You can attach every one of those sentences to something that's going on at the level of the equations. But, once or twice in that chain of sentences, I said things that you just have to trust me, that they sound kind of good, but why does dark energy have a negative pressure, and why should negative pressure, you don't know why these things are true. Why? So it's sort of, it gives you a warm and fuzzy feeling that you understand something, but you wouldn't actually be able to defend your understanding to someone else who did hear the same explanation as you did.
Yeah, so you just have a watercolor picture, maybe, as opposed to
I think it is
details.
It's a very, it's a very, very non-trivial issue. What is the best approach to better understanding that people who are non-experts should make when they're learning science? And every one of us is a non-expert at most areas of science, right? I'm a theoretical physicist. I'm not an expert about biology or geology or whatever. So I have the same exact issues as anyone else does. I would like to understand something about, let's say, the origin of life or global warming or something like that. And I'm not going through the equations. So my understanding of it will be heuristic. It will be based on approximations and translations into English. And I want that understanding I have to be as good as it can be. And it doesn't need to be so good that I can redo the models or write a code for myself or do an experiment for myself. But I want, if I try to explain it to somebody else, I want the basic ideas that I would get across in my translation to be more or less accurate.
Yeah. And as far as the response of the public to various issues in physics and what's happening, big ideas in physics tend to get people really excited. So we were talking about neutrinos earlier, and people who are not normally interested in science or physics, people I didn't expect to hear talking about neutrinos. We're talking about faster than light neutrinos. Right. So this was a really big attention grabber. And then, something like the Brian Cox lecture talking about everything being connected. That's something that maybe people can grab onto. And then you mentioned you've got a book about the Higgs boson that's going to be coming out. And once again, that's another story, another idea that people are really fascinated by. Mm-hmm. What do you think it is? Physics it's getting so much wonderful media attention lately. There's just these big. Is this just the time of big ideas? What's going on?
Well, I think that there's a couple things. One is that we're a little bit lucky right now at the time when we are talking about physics, because in particle physics especially, the last few decades have been kind of fallow. It's not been a lot of really surprising results. They're experimental results. There have been surprising results in astronomy, in other areas of physics, certainly superconductivity and condensed matter, graphene, atomic physics. But particle physics has been kind of quiet. It just takes big machines that cost billions of dollars and take decades to build to get to the energies that we need to achieve. So finally we're getting there, and that's a very legitimate reason to be excited with the Large Hadron Collider in particular. But the other thing is just that, we shouldn't be surprised that people are fascinated by physics. Every kid is fascinated by physics, right? They want to know how the world works. They poke at it. They set things on fire. They touch things they shouldn't. They put things in places they shouldn't be. They're curious. They're trying to figure out how the world works. And sometime, and you can pinpoint it. People do studies. Sometime around when you're 13 or 14 years old, this is beaten out of you, this innate curiosity. There's probably many, many factors that go into this. You're now interested in dating and grades, and the anxiety set in, and your body's changing. But for whatever reason, we suppress that natural curiosity, and we're taught, or at least we absorb from the society around us, that this isn't quite what we should be passionate about. So it's just a matter of rekindling that very, very natural human curiosity that, okay, we know what you're really worried about is, your job and your love life and your retirement and your kids, but carve out some space in your life for just marveling at how the universe works. And I think that people naturally do this. And, people like you with your podcast, this is a very useful way of reaching a couple people who couldn't be reached otherwise, who wouldn't get that little bit of science. The audience is there. The demand is there if we can get the good news to people in palatable and entertaining ways.
Yeah. Tell me about the new book that you're working on, Higgs boson, LHC. What's the angle that you're taking there?
Well, hopefully we're going to discover the Higgs boson. This is the idea. And, we had little tantalizing hints that we heard about in December from ATLAS and CMS, the two experiments at CERN at the Large Hadron Collider. And it's very realistic. I would say, 50-50 bet is you would take either side reasonably that by the end of 2012, they'll announce they have really, really good evidence for the Higgs boson being there. And like you said, people are fascinated by this. This is front page news in the New York Times and whatever. So trying to capture some of the flavor of why is this such a big deal. Leon Letterman wrote a book that he got a lot of flack for called The God Particle.
Yeah, I remember that book.
And, Leon himself says there are two groups of people who we offended, people who believe in God and people who don't believe in God. The people in between. But, the God particle is a name that physicists hate because it's nothing to do with God whatsoever about the Higgs boson, but it's an attempt to capture some of the importance. This is the final piece of the puzzle of the standard model of particle physics. The Higgs boson is the one thing we haven't detected yet, and we're hoping that it is the gateway to a whole bunch of things that we don't know about yet, to particle physics beyond the standard model. One of the people I was talking to for the book put it very, very well. If the dark matter in the universe is what we think it is, if it's a weakly interacting massive particle, it might not be, but that's our best guess, then the force that allows ordinary matter to interact with dark matter is the Higgs boson. Just like the photon carries the electromagnetic force, the Higgs boson carries its own force, and it's the force that interacts with dark matter. So that's important. It's the gateway to most of the universe in a very real sense. So we should be excited. I want to know the human side of the story and the physics side of the story.
I'm looking forward to reading it when you're done. That'll be so interesting. You mentioned earlier about the sigma levels, how 6 sigma is very significant and around 3 sigma is very interesting. With the data that's been coming out with about the Higgs boson recently, where are we in terms of sigma levels?
I would say that we're at 3-ish sigma. And the reason why we can't be too particular is because there's different ways to calculate it. There's just different ways to ask the question. And there's no right or wrong answer. It depends on what question you're asking. So the probability that this one experiment would have seen a signal in this particular place is, more than 3 sigma unlikely, not quite 4 sigma, but still is more than a 3 sigma fluctuation away from what you would have expected. But the problem is that you're doing more than one effort, right? If something only happens 1 out of 100 times, but you do it 100 times, then you're going to see it, right? It wouldn't be that surprising. So if you look for the Higgs boson in many different places, the probability of seeing it somewhere goes up, even if it's not there, if you know what I mean. So the overall statistical significance is a little bit less than that. And also there are 2 experiments, and the other experiment did not see as strong evidence as the ATLAS experiment did. The CMS experiment, which was actually in principle better tuned to finding it in that region, had weaker statistical significance. So I'm talking back and forth to people, and I think that most people are pretty optimistic that it really is there. And part of that is the data that we were given in December. A bigger part of it is that it better be somewhere, and we've ruled out most places it could be, and so we wouldn't be surprised to find it here.
Yeah, and this year they're going to be increasing the power on the LHC, so there'll be more data. There'll be
3 times as much data this year as they have so far in total, so at a slightly higher energy. So it's realistic that by the end of the year, once the LHC is a really amazing machine, and the details are absolutely fascinating. They don't run during the winter time because electricity is too expensive, right? I mean, DEPA is using its electricity for other purposes in the dead of winter. So they shut down. It gives them time to, tighten up the accelerator and give it a tune-up and so forth. So they're in shutdown right now. They're not collecting data, but they're going to start collecting data, and they're going to run through the year. And they will shut down again near the end of this year and analyze the data. So there'll be updates over the summer. Who knows what they will see? There'll be more updates at the end of the year. And hopefully they'll see something, because at the end of this year, I think according to plan, they're going to shut down for like 2 years. They want to really upgrade the accelerator so they can go to much higher energies when they turn back on. So we'll have some time to digest whatever it is that they tell us.
They're trying to give themselves a little bit of room to breathe so that they can actually look at all the data that they're collecting, the massive quantities of data that are coming out of that machine.
Well, it is also, it's the most complicated machine ever built by human beings, and it did blow up. There was an event, in September 1908. It exploded.
It had something to do with like a bird and a baguette and a man going back in time.
But, no, I mean, something overheated. The magnets are supposed to be very cool, and it kind of ran away, and 6 tons of helium flooded the floor and so forth, and it was bad. And it's because no one has ever done this before. So you should expect some missteps like that. Since then, it's been running amazingly well, better than we could have expected. But every time you do something, increase the energy, push it a little bit harder, something could break. So they're trying to be as cautious as they can. It's much better to get up there gradually. The Higgs will still be there tomorrow. It's not going to go away.
And in terms of the Higgs, there is always the possibility, even though it is the final particle to be found, everything seems to point towards a particle existing in a particular energy space. But if it is not found, do you have an alternate ending prepared for your book?
Well, no, my book is about that in a big way. In some sense, the point of the book is we've been waiting 30 years or 40 years, arguably, to do this. And if it's not, well, no matter what happens, we need to worry about the future of particle physics. The LHC costs $10 billion. And the $10 billion is not lying around. It's not, by the way, $10 billion per year. It's $10 billion spread over many, many years. So it's chump change compared to many other things that we do as a society. But it's still very, very difficult in this climate to get an agreement to say, well, let's do another one of those at twice the cost, to get to even higher energies. Yeah. So if we don't find the Higgs boson, if we find nothing at all, number one, most physicists would be really, really surprised. It's just really hard to imagine a theory of physics in which you truly find nothing at the LHC. There can be surprises, so you have to do the experiment, but it's actually just hard to imagine finding nothing. But if you did find nothing, it would be a time for, thinking deeply about, is there a different way to get at these problems? Is there some different technology that we can use? Because no one is going to give you money to build an extension of the LHC if the LHC finds nothing at all.
Right.
I don't think that's a likely scenario. I'm not worried. I have other things to worry about besides that. But it's something that, people are betting their lives' work, quite literally, on this project.
Yeah. Well, it's not the only thing that the LHC is working on. There are many experiments, and it's working on all sorts of questions, which is great. But this is the big one.
And nature is always surprising us. So.
Yeah, always, always. Sean, thank you so much for joining me today on the Science Hour. It's just been really great talking with you.
My pleasure, Kiki.
You're welcome. And anybody who is interested in finding out more about Sean Carroll, the books he's written, his blog, you can head over to preposterousuniverse.com, and you should be able to find links to more information there. Lots of fun stuff. I'm Dr. Kiki, and this has been Dr. Kiki's Science Hour. And next week, we're going to be talking about the science of willpower. That's right. How do you have a will to do things, willpower? How do you keep from doing things? Right. Where there's a will, there's a way. And I hope that you will join me next week. Until then, I hope you'll join me on the internet. You can enjoy my sciencey pursuits on Twitter. I'm Dr. Kiki. I'm Dr. Kiki on Facebook, Kiki Sanford on Google+. And you can subscribe to this show on iTunes, or you can go to twit.tv/Kiki for past episodes and other ways to subscribe. Additionally, I also do This Week in Science on the TWiT network, and so I hope that you'll check that out. There's a spin-off to this show, the news at the front half of the show, the sciencey goodness at the front. Well, if you don't have time to spend an entire hour listening to these wonderful conversations, you can at least get the news weekly. We are spinning off Science News Weekly with just the news. So you can just download that once a week. Science News Weekly, it's twit.tv/SNW. Anyway, I will see you next week. Thank you very much for tuning in my Science Hour. Remember, all I ask is 1 little hour a week. That's it. And I hope that 1 hour a week makes your world a whole lot more interesting. Now it's time for your science meditation of the week. Thanks to Phil Plait, the band astronomer, for leading me to this one.
20,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenoir, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
Yeah, I love the things that we used to do.